Okay, let's try this again. We were going for it correctly.
Yeah.
So I resubscripted this to make it a little more helpful. So this says the force on particle 1 by charge 3. This says the force on charge 1 by charge 2. I think we were doing it correctly, so we should have done, and I'll rely on you guys for the calculator work. So KQ1 is 20 microcoulombs. Q3 is 30 microcoulombs. And this is 9 times 10 to the negative 9th, right, with constant, and 0.25 squared. Somebody have that yet?
Well, I did it with K is the original, not the exact. But I had 8.496 times 10 to the negative 4.
Let me get some confirmation. Guys, can you tell me what this is? Did we get this number yet?
That is 86.4 newtons.
That sounds reasonable. Right, so I'm not doing that part yet though. So we're just getting like Jake said. This is exactly what Jake said, so I should trust him. Let's see. So then this one's going to be negative 10 and positive 20. And that's the same distance away. So that number, can somebody give me that number? Should be less, right? This one should be less, shouldn't it?
28.
Its magnitude, 28.
28.
0.8? Makes sense that that's about a third, doesn't it? Is it in fact exactly a third?
Yes, but it should be negative.
I think it should be.
Yeah, it should be.
And it should be negative because it's an attractive force, right? That's what that means. Okay, so we've got the two magnitudes. What we really want to know is like what's the net effect of those magnitudes, right? So for that, I think we need to, do we need to split them into components or not? Think about it. I think we do need to split them into components. Why can't we just like take the square root of them squared right now?
Because that's negative.
Because yes, you guys hear Sheldon? Like I'm tempted right now to just look at these and say, can't I just take the square root of the two acting forces squared and like get it? But the reason that wouldn't quite work is because like they don't have any direction right now. If you look at the situation, I tried to draw this vector a little bit longer and this vector a little bit shorter. Where do you think the net vector is going to go? It's not going to like be right in the middle, is it?
A little bit up. It's going to be a little.
It's probably going to like have more up, yeah? And like how long do you think it might be?
Like,
Longer.
like a little bit
I
shorter.
don't know. It's going to be adding or not.
Well, the x components, are the x components going to be adding or like opposite each other? The x components are adding, so I bet it's going to be maybe a little bit longer that way and up a little bit, something like that maybe?
Or could it be just about the same?
Well, I mean, it's something, I think it's, yeah, maybe it'd be just about the same, but I think it's going to be up and a little bit longer. That's my hypothesis. So let's split it into components and see what we get. So when we split it into components, we want to go like this, right? So what is the x component of just that top vector? It's going to be that number cosine, because we're just going like cosine, that's the x component, right? Like that. So cosine of what? What's this angle right here? We need this angle. What's this angle?
It's 60, isn't it?
I guess we can go up here and look.
Yeah, because it's.
So it's an equilateral.
If this is 60 because it's equilateral, how much is this one?
30.
That's
No,
all right.
No, it's 60.
Is it 60
It
or?
would be 60 because
It's
then
60.
It's 60, right? Because we're saying from here to here. Yes. This would be like straight down is 30, so 30 plus 60 is your 90.
Oh,
Yeah, sneaky, right?
Yeah.
Very sneaky. So if that's 60,
Because it's 180.
then this will be 180, right? So this would be 60. Okay. So you might have to be a little careful there. So this is going to be 60 indeed. And I think that down, we now already have our down too, right? So for this one, we'll have a 60-degree angle as well. Yep. Anyway, so that was a little bit sneaky. So cosine is 60 there. If we want that vector's y component, that's just going to be the part that's going up, right? So positive on this one. You can either do like 120 degrees, or I just like to think positive or negative personally. This is going to be positive, isn't it? So it's going to be 86.4 sine of 60. And then the other vector, x and y, what are its x and y going to be? So x on this vector is going to be negative or positive. I guess it depends on our sign convention. Was this one really negative or positive? Wasn't that one really negative? I think we should put a negative on there. I'm going to put a negative on there. Or if you do the cosine in that quadrant, isn't cosine negative on this quadrant over here? As opposed to over here? Anyway, so I think this one's also going to be negative, except its magnitude is a little bit less. So 28.8
So it's negative.
cosine of 60. So
It's the opposite of opposite.
do we want to make it like negative of negative there?
I don't know.
Let's just think about it. It's a good question, right? Do we want to like change this negative back into a positive? Think about your overall effect. This guy is pushing that out that way, right?
Because we
This
know-
guy is trying to pull it this way. Shouldn't they be like in the x direction accomplishing the same thing?
Both negative.
So I think they should either be both negative, or if we want to turn it around, we could say they're both positive as long as we're consistent.
It was sort of like we already incorporated the negative when we drew our little diagram.
We did.
Because that's what we were thinking
We did.
about.
So you don't want to do it twice, right? That's why you want to keep going back to your diagram and making sure you're consistent there, I think. That's the way I think about it anyway. Good. All right, so what about this one? Y component of this guy coming straight down, that's going to be 86.4, negative or positive?
Wait, wouldn't it be 28.8?
Oh,
Yeah, there we go.
thank you. And it's definitely opposite of what this one was, right? Because they're going to try to cancel each other out a little bit. And that's what we were having trouble with when we were trying to do them as a whole. So sine of 60. Okay, so I need some numbers.
Negative 43.2. 74.82. Negative 14.4. 24.94.
Okay. So, how do we get our final answer? We've got everything we need. Just got to use those numbers, combine them. How are we going to do it?
Just like you would do with that
There's some.
So we just say the overall force that we're experiencing at this point is,
You could even write them out in vector notation first if you wanted to.
I could, right?
It's not really necessary.
But it's going to be the square root of something squared here and something squared here. What am I going to put in here?
F13x plus F12x.
And the x forces and
Yeah.
y forces.
This guy, the x forces and y forces added together, right? We agreed that these are going to be like, see how the squared's going to take care of that anyway? We're just getting like a magnitude answer here, aren't we? That's what this gives you, is a magnitude answer. So what is that going to be? Like 60 something squared? What is this number? 57.6. Thank you, Todd. And then it's going to be squared, so we didn't even care. And then this one and this one. What's wrong with my answer? I see a mistake. Thinking about my diagram, I know I shouldn't be like getting all that in the y direction. Part of it's going this way, part of it's going this way. So this one was supposed to be negative. So when we put those together, what do we get? Like
49.88.
49.88. So that's the component that the y is providing. They're both providing the x components. You had to split it into components to get this. You can't do this another way, unfortunately. So what is the overall answer? And we'll see if it makes sense with what we thought, right? Hopefully it's going to make sense with what we thought would come out. This is like the heaviest math part of this whole class right here, right? Like, there's no heavier math in this class.
76.19. Or 196 actually.
Newtons?
Yeah.
So Do I have confirmation from Jake, for Jake?
Yes.
Thank you. Does that make sense? Let's think about it. So the individual forces were 86 and 28. It was a little bit weaker, so I guess it did cancel it out a little bit. That guy down there, cancel it out a little bit. Should we do the angle for that guy? To see if it's actually where we thought it was? Let's see. So tangent of theta is, and we have to take the x and y components, right? So let's think about this. So somehow we got to go back here and say the tangent of theta is y over x, right? So what was our y contribution? When we did the 74 and the negative 24, we got 49. More trying to go up, right? 49.88, and then x components, we had them both going that way. That was our 57.6. Take an inverse tangent. Use some crazy notation. Curious what this angle is. It's almost the inverse tangent of 1. Alright, this is almost 1. What's the inverse tangent of 1? What angle has a tangent? 45 degrees. So maybe it's even up higher than we thought it was.
So it's 41 degrees.
41 degrees?
41.
So let's see if that makes sense. So that's saying like this guy's like 41 degrees above. In other words, he's pretty close to that one. But remember, this one was a lot more powerful, right? This charge was 3 times what that charge was, even though they're like the same distance apart. Why does it make sense that this guy's like totally overpowering that guy almost? Why? What about?
Their directions are sort of opposite each other.
Yeah. There's something else in here. Well, I'm just arguing. We were kind of predicting a little bit that it would just barely overpower it in terms of its effect on the direction of that vector, right? Why did it come out even stronger than we thought? Remember, in Coulomb's law, you're dividing by r or r squared? You're dividing by r squared, aren't you? So since these were like the same distance apart and this one was 3 times as strong, that r squared kind of blows that guy off the map. That's all I'm saying there. He kind of like limits his effect at all since he's not the same magnitude. Okay? So should we do number 2 as well? I think not. So let's do the center of the triangle. So we'll not do this part. Or we're gonna spend the whole class up here. So these do take a little bit of time. Believe me, if you can do this, you're going to be able to do calc-based physics and stuff easy too. So no worries there. So let's see. Center of the triangle. So I'm thinking, what is the force due to all 3 of those now at the center of the triangle? So we're going to have to do like 3 parts, right?
And x and y is for all of them.
And x and y is for all of them. Do you guys want to try it yourself? Should we look at the geometry a little bit first? Then I'll let you guys have a second.
So the magnitude of the E fields, the data can do that probably in a second.
Yeah, let's just go down here. Let's just do number 2. Let's do not the force, but the field there. Okay? So let's do the field at the center of the triangle first, and then we'll move out and do at this spot over here in a second. Okay? So the E field, instead of using Coulomb's law, what is our formula for the effective point charges? It's actually easier than using Coulomb's law.
Q over r squared. With
K.
K in there.
KQ over,
R squared.
it's not an inverse square, it's just r.
Yeah, it is.
Isn't it?
It's just R.
Is it r squared?
Yeah.
Oh my gosh! Sorry, I thought it was a regular. Okay, so what's the E field at that spot? So I'll give you a second. You're gonna have to do all 3 charges. Think about how they're interacting with this guy. See what you can do with it, and then we'll do it together. So whether you're doing fields or forces, I mean, you're just using a different law. You're using Coulomb's law versus this thing, which is almost exactly Coulomb's law. It just doesn't have two charges, right? Why doesn't it have two charges in it?
Because you're not acting on a separate charge, you're acting like this spot.
Yeah, it's just like there is no other charge. It's just a spot. Yeah. Other than that, it's we're doing just about the exact same. K is 9 times 10 to the negative 9th, isn't it?
No, to the negative 9, just to the right.
To the 9th?
That was 8.988.
Yeah, that's it.
Uh,
But they rounded it up.
We're just gonna round it.
We're just rounding now? Not very precise anymore. Never.
That means you only have one significant digit, right? We only have one significant digit if we round like that. Got to do some geometry on this one, huh?
Touche. Not particularly excellent geometry, I think. I think it's easier to just pick a degree for your theta, because it's half, right? So this goes in the middle, it's half 60, so theta there is 30, so you can use that.
Oh, for this?
Yeah.
Okay,
Right.
I'm just going for how long this is.
Right, that's,
But yeah.
so we did it a different way.
Yeah, if you use sine or cosine, it's smarter.
27.95.
Oh, mine's in my. Gosh, I'm off my game.
Don't you have to divide that by 2 though, Mr. McGee? Or you can use it as...
Yes, I do. Sorry if your geometry teacher was giving you easy problems. They weren't really doing you a favor, were they?
Well, seeing, I have no idea what my geometry teacher was doing, because most of the way through geometry I wasn't paying any attention whatsoever. Remember that assembly in the corner of my junior like all the way through?
Yep.
So I use your hypotenuse.
Literally did nothing.
We do a little bit more. We do a little bit more.
That's okay. It's just fun.
We do a little
But what I
Not a whole lot though.
It would be. Oh, hey, we just.
Okay, do we all agree on what I have up on the board so far?
Yes.
So the electric field, due to this charge, we have to do them separately. At that spot, this is the radius. So you have to take like half of this triangle. So I went half the triangle, used Pythagoras, and then I cut that in half. There's my cut in half, and that's that distance for that charge. Then you put the charge in and you put the Coulomb constant. I think that that is the same distance for all the other three, isn't it? Because if this is that, we want to go like this. I think an equilateral triangle, these are the same. These distances are the same. I mean, you could compute it by doing some more triangles and stuff if you wanted to, but I don't think you need to.
Because the hypotenuse should be like this. It's 25 squared minus 25 squared.
I don't think it. What did you get for?
Yeah, we got 14.43 for our R.
25 is C, that should be minus, yeah. What is this? Sorry,
What'd you guys get?
I am off.
21 point.
But is the center of the
Six
triangle
five.
halfway up the height?
21 point.
6.5.
Obviously, it's not good to take my word today.
10.8.
That's
Divided by 2.
Is still not what you have
we have
We got 14.43.
for the whole thing?
For, no, just, oh, is that like top to bottom?
Yeah, this is top to bottom.
Because
like that.
oh.
But then divided by 2 is
the center of the triangle.
Should I be dividing by 2? Let's be careful here.
No.
Crap. Oh my. It's the day of mistakes, but I think it's actually good to make all these mistakes because I bet you guys are going to make them anyways.
We just used.
Maybe you're just better than me though.
Yeah, we use.
It's not divided by 2.
We use a triangle. We use like the bottom right-hand triangle basically, where it's
Yeah,
12.5 and 30 degrees for the angle.
that's smarter.
And yeah, we got 4.
We could do it that way. Can we do it our way still?
I guess.
Because like this point is not halfway. If it looks like halfway, like I was thinking it was, that's not true. I think it's like right here. You know what I'm saying? So can we even do it that way? I'm trying to think. Anything? No? I don't think so. I don't think I can even use the triangle I was thinking about.
There's something with the Euler's formula that says that's.
Yeah, there's some weird geometry thing which we didn't learn.
Okay.
that tells you where that's at. But
'Cause it's like
what
2/3 of the
Jake
way
is
down.
saying is he used this, right?
Yeah.
He used this guy. That's a much smarter choice. This is 60 degrees, so that's 30 degrees. You know, this is 12.5, so you can solve for
Yeah, it is 2/3 of the way of the
Wouldn't that
height.
just be some
you can
cheese?
solve for x.
Cosine 30 is x over 12.5
So x is 12.5 over cosine of 30,
Yep.
which was 14.
14.43.
So this is 14.43 squared, 14.43 squared.
443 squared. Because it's 7 meters. So you have to convert to meters.
You guys have learned something this year. So happy. So that when I let you down, you catch me.
So do you just add up the electric fields?
Right. So should we just add those up to figure out the net? That's the same question we had on the last problem.
X and Y combined.
Yeah, you do.
If these were all like the same charge magnitude and stuff, could we, and like they were all positive or all negative, could you just add them up?
Will they be?
As long as you
net
thought
force
about
will
it,
be
I think,
zero?
yeah, you could probably like,
Yeah, 'cause they're
probably
all-
like, yeah, you could probably like say the net force would be either 0,
Maybe some.
Yeah.
something like that, some kind of symmetry. But since these are like all different sizes, because I'm just mean,
So we gotta find the X.
I
and
think
Y
we do have to find the X and Y components. So I don't know. What do you guys think?
Those
If
are
this is a
easy.
positive test charge, where do we think it's going to go? If these guys are pushing it,
It's gonna go to the
this
left.
is pulling it.
That way, but down a little bit.
So like push, pull, it's going to be that way, isn't it? Okay, that should make sense. So hopefully we get something like that. I'm guessing it's going to be stronger than any of these. What are these answers? Can somebody tell me?
One is 8.6 times 10 to the 6th.
It's a lot of newtons.
Is negative 4.3 times 10 to the 6th. Negative 4, yeah. And then 1.3 times 10 to the 7th.
These aren't newtons, are they? What is it?
They're probably like newtons.
It's a field, right? Not a force.
Newtons per coulomb.
Just go back to the equation
What
real
is it,
quick.
Newton meters per coulombs? I don't remember.
E equals F times Q or divided by Q?
Over Q. So it's newtons per coulomb.
So you notice how you can know your units real well, right? Just by knowing the basic relationship between force and field. Okay. So I guess, yes, we're going to have to do X and Y components, and I'm just going to have to take this again.